So with this understanding of what we're going to do, we can actually examine the candidate elimination algorithm. The intuition is very similar to find S, except we don't make some of the same assumptions that everything starts out as negative. We're going to start off with a most general and most specific hypothesis as sort of the bounds of the problem, which will admit every possible hypothesis. Okay? Now, when we observe training examples, we're going to change the hypothesis set of valid hypothesis, that means our version space, to minimally generalize or specialize those two boundaries in order to remove any inconsistent hypothesis from that version space. We're going to start with a most general hypothesis, which we can write. In our case, for our enjoyed drink problem, would look a little bit like this, right? Meaning that I accept any drink that you give me. They're all good for me. And a maximally specific hypothesis with an H, okay, which would be nulls everywhere. Right, which basically means I hate all of the drinks, okay? So this means everything is positive, and this one means all negative. So let's look at the case of the candidate elimination algorithm. It's basically going to have two parts, one for the positive instances and one for the negative instances. If it's a positive instance, what we need to do is something very similar to what the find S algorithm, which is to generalize it. What we're going to do is take any hypothesis that's inconsistent with it and remove it from our general data set, our general hypothesis set, okay? Then what we're going to do is take, for all of the specific examples, okay, for all of the specific hypotheses in our specific hypothesis set that's not consistent, we're going to remove it and then try to generalize, just like we did with find S, each of the versions of S that is going to be minimally going to generalize such that it's going to be consistent. And that we know that some member of G is still more general than the hypothesis that we're going to add. Okay? And then finally, as a post-processing step, we're going to remove from our specific hypothesis set any hypothesis that's more general than another hypothesis that's in S, so that we can keep that boundary nice and crisp. Now, I'd like you to compare between this slide and the previous one. The only thing that we've done is we've switched all of the valences of things around, okay? So let me just show you what those are. Negative, S, G and G, okay? G from G, G, specialization instead of generalization now of G, such that the same member of S now is more specific than H, and then remove from G anything that's more specific than any other hypothesis in G. Okay, so we've just flipped all the valences of the descriptors around. Okay, so let's go through this again, all right? If X is a negative example, what it means that our G boundary needs to be less general. It needs to reject this particular training example and say that doesn't fit in the concept that we'd like to have, okay? So to do that, basically what we're going to do is for each of the ones that are hypotheses that are in capital G, that means our general boundary, we're going to look at each one of those and basically try to specialize it such that it's not going to accept this negative example that we picked out in this round, okay? You have to do it in such a way that H is still consistent with X and that some member of S is more specific than H, okay? And then we, again, do the post-processing step where we make sure the G boundary is crisp, that we remove any hypotheses that are more specific than another hypothesis in G. To understand candidate elimination better, it's probably easiest to go through a trace of the algorithm. Let's take a look at several training examples. We're going to start first with S0 and G0 set to the most general and the most specific hypothesis. Okay? Now the first two training examples are positive, so the positive version of the algorithm holds. Let's take a look at X1. X1 is the same drink that we saw in the previous part in the pre-lecture. Okay? When we're exposed to that, we have to remove from S any hypothesis that's overly specific because it's not consistent. That means this is going to go away. Okay? And what we're going to do is take that S that we just removed, okay, and make a generalization of it, okay, such that H is consistent with X, okay, and that some member of G is more specific, more general than H. We actually have that very easily. We're going to specify all of the nulls to their exact values. And now we have our S1. Our G1 never changed because when we're dealing with positive examples, we don't need to change the general boundary because they're positive examples. When we come to X2 in the second part, we see that the third modifier is changed, okay? Therefore, we have to generalize that one, okay? And again, our G2 hasn't changed. So this is the state of affairs after seeing the first two positive examples. So the third training example is a negative example. And this means that the second half of the algorithm that deals with negative examples is going to be used. Right? Here what we want to do is go through and expect all the general hypotheses, okay, all of them that are within the set G. Right now we only have one in the second one, all right? And remove that one that's not consistent. It's not consistent because this says, I like all drinks, but it's patently clear that there's at least one drink that the target concept doesn't prefer. Okay, so this is no longer consistent. We have to get rid of it. And how are we going to get rid of it? Is to remove it from G, but then add all of the minimal specializations of G such that it's consistent with consistent with our input data. This means we could generalize the first, the second, the third, the fourth, the fifth, or the sixth example, right? All of these are specializations, but not all of them are going to be consistent. And we have to make sure that some member of S is more specific than H, okay? So that only admits these three examples as possible, okay? So this one over here is a specialization of the sixth attribute, right? Because you can see they conflict, right? Dabao and lim are different, so I'm going to have to fix these up, okay? And we are going to remove from G any hypothesis that's more specific than another hypothesis in G. But you can see all three of these here are partial orders, all right? They're equivalent. So there's no way to remove any one of them because all of them are equally specific. Let's go to the final step. The final step is to go back to the first portion because we have a positive training example. So again, the first half of the algorithm dealing with positive examples applies. Again, what we're going to do is go to the specific boundary and specialize it. But we also, in this case, have to do some movement on the general side too. Why is that? If we take a look at this particular one, we can see that we actually have to change this particular one because of the restriction between this one and this one. We have a drink that needs to be generalized here, okay? And so we cannot hold this general concept any longer. It has to be eliminated. and we're left with just these two. Okay, then what we're going to do is going to do the main loop, and we're going to remove from S any of the hypothesis that doesn't fit anymore. So we're going to throw this one away. There's only one member of S, and we're going to find the minimal generalization of it. Yeah, we have to generalize two things. Okay, here we have ones that are thick and weak, and here we have ones that are to drink here and to take away. So you can see that these two modifiers get changed to question marks. And now we have, at the end of round 4, found the boundary that is the same as the one that we described earlier. So with this, we have our S4 and our G4, and we can see all of the intermediate hypotheses are sandwiched between our specific and general one. We don't have to enumerate them, but if we did, we would see there's actually a total of 6 different hypotheses. Again, 1, 2, 3, 4, 5, and 6 that are consistent with the data set.